Now that we have discussed about different types of number systems in the branch of mathematics, the real numbers, the rational numbers, irrational, integers, whole numbers and natural numbers. Now let's see how we can represent the irrational numbers which are not the exact numbers on the number line, the real number line. Let's recap the irrational numbers which we have discussed in the previous sessions. Irrational numbers, as we have discussed, are the elements which are written in the form r minus q. So all numbers which are not rational or which cannot be expressed in the form p by q, failing both the tests pq belonging to z and q not equal to 0, is how we define irrational numbers. So let's see how these irrational numbers can be exactly located on the number line through the exact distances. For example, I take the irrational number root 2, which is clearly an irrational number. Now, when I convert this into the decimal representation, we know that root 2 is approximately 1.414 and dash dash. Now, because this is not an exact number, even in its decimal place, we will try to use some geometrical construction methods to represent root 2 on the number line through the exact distance. Let's see how we can do this. Before we just try to construct root 2 on a number line, let's try to recap with some geometrical constructions which are useful in construction of root 2 on the number line. For example, I take a square of side 1 unit. So here I have a square of side 1 unit with all sides being equal with 1 unit on each side. Now here I try to extend the diagonal from one corner to the other corner. So we know that this diagonal forms the hypotenuse for one of the right angled triangle taken on either side of the diagonal for the square. Now this being a right angled triangle, let me say this is A, B and C. So ABC forms a right angled triangle, right angled at B, with AB equals 1 unit and BC equals 1 unit. Therefore, by using Pythagoras theorem, I have AB square plus BC square equals AC square, and which on further representation of the given values gives me 1 square plus 1 square is equals AC square using Pythagoras theorem. Now when I further simplify this, I get this to be AC square equals 1 square which is 1 and 1 square which is 1, when on further adding up gives me AC square equals 2. That implies my length AC, which is the diagonal of the square, equals root of 2, is how I get the root 2 out of 1 unit of the square. So this dimension of the diagonal being root 2 is what we utilize in representation of root 2, which is an irrational number on the number line. So let's see how we can just take this further into geometrically constructing root 2 on the number line. Let me take the number line before we construct root 2 on the number line, or representation of root 2 on the number line. So here is the real number line which extends from minus infinity to plus infinity, with all the points on this line being the numbers of the real numbers, or the real numbers of the number system. So here I have the real number line which is represented through the line and called the number line, and here I have exactly in between the neutral 0, from where on the right side you have all positive values, on the left side it's all negative values. So let me just proceed with the right side of the values, which is 0, 1, and next comes 2 and 3 and so on and so forth till infinity on the right. Similarly, on the left I have negative 1, negative 2, negative 3 and etc. unto the negative side of the infinity. Now let's try to see how we can construct root 2 on this number line using the previous discussion of the square which gives me with the dimension of 1 unit and its diagonal, which gives me the distance of root 2. So let's see how this can be transferred into the number line to get the same root 2 on the number line. So in order to do that, I need to have this diagonal placed on this number line, which is possible by constructing a square of 1 unit. So here is 1 unit. So I construct a square of 1 unit on each side in this form. So once I construct a square of 1 unit starting from 0 to 1, that is a square being built on the number line, I try to join this diagonal from one end to the other end. Let me just mark this as A. Now OA is the diagonal for this square, which we know indirectly is root 2. Therefore, I just transform this dimension into root 2 out here. So I get to be OA equals root 2 units using the concept of the square, which we have already discussed in the session. Now with this root 2 units, now I take a compass and just point it at O and put the compass at A and just draw an arc. So when an arc is cut, I just get an arc which cuts the number line, indirectly stating that this forms a circle with same radius. Therefore, the radius of root 2 units made by the compass is nothing but the radius of the same root 2 units as made by the compass on the number line. And thus, we get the distance root 2 out of the square diagonal in this manner. So when we would like to construct root 2 on the number line, we try to first construct a square of 1 unit on the number line from 0 to 1 unit, and then take its diagonal, measure the diagonal with the compass, then draw an arc such that the arc cuts the number line. And the point where the arc cuts the number line, I denote it with B, and OB is root 2 for sure, because the radius is the same for any part of the circle from its fixed center. Therefore, my OB as constructed from the arc is also root 2 units because it is the same radii, the same radius concept. And therefore, my distance on the number line from O to B is what is the distance, which is an irrational number, root 2, which can be represented on the number line in this manner of constructing through the geometrical square diagonal. Next, let's see how to represent the irrational number root 3 on the number line. Of course, root 3 has the value which is 1.732 and so on and so forth in its decimal representation. So this value root 3, an irrational number root 3, I would like to represent on the number line, just like root 2, how it can be represented on the number line. So let's see what geometrical concept can be used in case of root 3 to construct on the real number line. So here I have, say for example, I take a right angled triangle and I have this to be an isosceles right angled triangle, 1 unit and 1 unit, and therefore of course it's an isosceles. So these two sides being equal, it is an isosceles right angled triangle such that the two sides are 1 unit each. Then obviously by using Pythagoras theorem, we know that the hypotenuse is root 2 units, as we have seen in the previous session of the diagonal of a square. So this being root 2 units, let's see how we can develop root 3 using this root 2. Imagine I take the point OAB and I try to take the point O and I construct a line perpendicular to OA and passing through A. That is, I draw a line through A perpendicular to OA, the side OA of the triangle OAB. So here I construct exactly with the distance being 1 unit. So this is exactly same as this of 1 unit. So here I mark this to be C. So C is the point which is exactly 1 unit from A and which is perpendicular to the side, the hypotenuse OA of the right angled triangle. So now I have the side CA which is 1 unit, and I have the side OA which is √2 units, as we can clearly see through the diagram. Now with this, let me join C to O. Say I just join C to O out here. Now let's try to calculate the dimensions of the side OC which is joined for this triangle ACO. Now let me just focus on triangle OAC and let's see what we witness from this triangle OAC. As we can see the triangle OAC, we see that AC is 1 unit and OA clearly is √2 units, is what we have from these two dimensions. And clearly this being 90 degrees, it's a right angled triangle, and therefore we have the Pythagoras theorem which comes into existence. Triangle OAC is a right angled triangle, and therefore this being a right angled triangle, we are going to focus on the Pythagoras theorem. So let's see what happens with Pythagoras theorem applied out here. So we know that in right angled triangle OAC, the hypotenuse OC square is sum of squares of other two sides, that is OA square plus AC square. And then when I further substitute the values, I get this to be OC square is equal to OA, which is √2 whole square, and AC, which is 1 whole square, which on further simplification gives √2 whole square. We know that √x into √x, which is √x whole square, is x, because the root and the square both get cancelled, and therefore I get x. Similarly, √2 times √2, which is √2 square, is 2, and 1 square, which is 1, which is finally 2 plus 1, and that is equal to 3. Now in this case, when I further simplify this, I get this to be OC square is 3. That implies my dimension OC is square root of 3. When the square comes out here, it comes out as √3 units. So this is how I get the dimension of OC. Constructing or locating √3 on number line, we use this geometrical concept of the triangle, and finally we get the distance OC, which is √3 units. And this is how we locate this on the number line. Is how we just understand geometrical construction of √3 on the number line using the right angled triangle, and most importantly the Pythagoras theorem of the right angled triangle.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.